Hey guys, welcome back. In this video, I'll be talking about polar coordinates. And we'll see how to describe certain regions on the XY plane in terms of these coordinates. Now, sometimes a plane region D may not be so easily described in terms of the usual X and Y. In other words, we may not have a nice description of D as a type 1 or type 2 region. And consequently, we may not be able to compute the double integral over D in terms of the usual X and Y. However, in such cases, sometimes they may be conveniently described in terms of the polar coordinates. So later on in the course, we'll look at how to convert a double integral in the usual X and Y to that in the polar coordinates. Anyway, for now, let us look at how to describe certain regions in terms of these polar coordinates. So suppose we have a point P on the plane whose coordinate is xy. It turns out that we can represent this point by using another pair of variables denoted by r and theta, where the variable r is the distance from the origin to the point P, and theta is the angle from the positive x-axis to the straight line joining these 2 points. And this is true for all the points on the plane. For example, if we have another point here in the 4th quadrant, then the variable r representing this point will be the distance from the origin to this point P. Okay? Now the angle for this point will be measured from the positive x-axis. Alright, therefore the variable r is always non-negative because this is a distance, and the angle theta is always between 0 and 2 pi. Next, let us look at the relationship between the xy coordinates and the polar coordinates. Well, that can be easily obtained by looking at the right angle triangle over here. Using elementary trigo, notice that sine theta from this right angle triangle is equal to the height of this triangle over the hypotenuse, and likewise cosine theta is the base of this triangle over the hypotenuse of the triangle. So after rearranging, we have the first 2 equations over here. And in fact, these equations hold for any values of theta between 0 and 2 pi. Now to get r in terms of x and y, notice that the variable r is just the distance between the origin and the point. So using the distance formula, we get r as being equal to the square root of x squared plus y squared. Okay? Now to get the last equation, we are going to divide the second equation by the first equation. And in doing so, we have y over x being equal to r sine theta over r cosine theta. Well, a word of warning here that this equation holds provided x is not 0. Otherwise, the fraction doesn't make sense. You follow me? When do we have x not being equal to 0? Well, this happens precisely when we are not on the y-axis. You see, the y-axis is the equation x equals 0. So as long as we are not on the y-axis, we have x being not equal to 0. So the equation here holds provided we are not on the y-axis. And after simplifications, we have this being equal to tangent theta. And so theta is the inverse tangent of y over x, provided x is not 0. Alright, let us now look at some examples. Here we have a region bounded by the unit circle x squared plus y squared equals 1. and we want to describe this in terms of the polar coordinates. Let us start with the angle theta. Whenever we have an equation, theta being equal to some constant k, for example, then this equation represents a ray coming out from the origin. You see, all the points on this ray will have the angle theta being equals to that constant k. So in order to find the range for theta for this region R, we are looking at all the rays intersecting the region, and it seems that we need to take all possible angles so that these rays will intersect the entire region. Okay, and hence theta is in the interval from 0 to 2 pi. Next, let us look at the variable r. Whenever we have the variable r being equal to some constant k, for example, we are looking at all the points having distance k away from the origin. In other words, the circle of radius k represents the equation r equals k. This is because all the points on the circle of radius k must have the distance r being equal to k. In order to determine the range for r for the region here, we need to identify those circles that intersect the region. It seems that we have to start with the origin because the origin is contained in the region. Now, by slowly increasing the radius of the circle, we are covering the entire region R until the radius of this circle is precisely 1, in which case we have arrived at the boundary of this region. You follow me? Hence, the range for the variable r is between 0 and 1. And finally, these two sets of inequalities determine the region R in terms of the polar coordinates. Let's do another example. This time we have a region bounded by two circles above the x-axis. The smaller circle is the circle of radius 1, and the larger one is a circle of radius 2. Right, let us determine the range for theta. For this, we are looking at rays going out from the origin and intersecting the region. It seems that we have to start with this one here, and slowly, by increasing the angle, we are having rays cutting through the region R. And finally, we have to stop when we reach the negative x-axis. This is because beyond this point, our ray will not be intersecting the region, and hence theta varies from 0 to pi. Alright, let us now determine the range for the variable r. For this, we shall be looking at circles intersecting the region R. First of all, notice that any circle of radius smaller than 1 and bigger than 2 will not be intersecting the region R. In fact, the circles that intersect the region R are circles whose radius are between 1 and 2. Do you see that? And therefore, the range for the variable r is between 1 and 2. So together with the range for theta, this will define the region in terms of the polar coordinates. Alright? Okay guys, that's all for now. See you next time.